This screencast is on solving equilibrium problems. These are very, very basic problems where we're given the initial concentrations of the reactants. They might also give you some products, but if they don't, remember that the initial concentration of all products is always 0 unless they specifically say otherwise. And they'll also give you one equilibrium concentration. We're going to use an icebox. I stands for initial, change, equilibrium, and we're going to use some stoichiometry to figure out the other equilibrium concentrations. Alright, so here is our problem, and this reaction occurs at 600 degrees Celsius, and we have the conversion of sulfur dioxide and oxygen gas to sulfur trioxide. So this one tells us that how many moles of each of those that we have, and it says it's in a 1 liter flask. Because we're dealing with concentration and calculating Kc, you would need to calculate your molarity, and with 1 liter as being the molarity, then we can just, our moles will be our molarity in this case because there is a 1 liter flask. They also give us that at equilibrium we have 3.50 moles of sulfur trioxide. Alright, so we have our equation like this, and then we're going to fill in what they gave us under the initial category. So they told us that we had 2 moles of SO2, and that's divided by 1 liter, so that's 2 molar. And then we have 1.5 molar of this, and we have 3 molar of this. The other piece of information they give us is that at equilibrium we have a concentration of 3.50 molar of this, again because this is all carried out in a 1 liter flask. Okay, given this information, what we can do is we can figure out the change from our initial concentration of SO3 to our equilibrium concentration of SO3. And so it gained 0.50. So whatever you're given the equilibrium concentration of, you are going to try and figure out the change. Now, the arrow in the center is kind of the great divide. And if we formed 0.5 molar of SO3, that means that we had to lose some reactants if we form some products. And so the sign of our change will flip if we go across the arrow. Now, the rest of it's going to be stoichiometry, and we're going to go across with the change category, or row of this icebox. So, the coefficients do matter. So I like to start with anything that has a 1-to-1 mole ratio first, or in this case, a 2-to-2 mole ratio. So SO2 and SO3 both have 2's as their coefficient, so it's a 2-to-2 or 1-to-1 mole ratio. That means if I gained 0.5 molar of SO3, that means I had to lose 0.5 molar of SO2. Now, I'm going to figure out my O2. Now this one is a 1-to-2, so 2 SO3s were formed for every 1 O2 that was used up. So we can go about it logically, and in this case we're going to end up losing just 0.25 molar of this one. You could also look at it just in terms of stoichiometry. If I have 0.50 molar, or again moles per liter, of SO3, for every 2 moles of SO3, 1 mole of O2 had to be used, and I'm going to end up with 0.25 molar O2. Okay, so now I have my change. It's very easy now to calculate my equilibrium. We're always going to add initial and change, so 2 minus 0.5 is 1.50 molar. And 1.5 minus 0.25 is 1.25 molar. Now I have my equilibrium concentrations for everything. This can now be plugged into my equilibrium expression to solve for Kc. It is going to be products over reactants raised to their coefficient power. Oops. So that will be squared, and this would be SO2 squared times O2. So I'm just going to plug these in. That's going to be 50 molar squared over 1.50 molar times squared times 1.25 molar. And that's going to give me a K value when I plug all of this in is 4.36, and we can just leave that without units there. That would be my KC, and then I could figure out my KP from that using the formula KP equals KC times RT to the delta N power.